we will go to the next talk, which will be given by Dr. Xiong.
Good afternoon, everyone. I'm very glad to be in this online meeting. It's really wonderful. Today, we are going to talk about thermal transport in long-range interacting Fermi-Pasta-Ulam chains. Actually, this is a joint work with Dr. Jing Wang and Professor Sigil. If you are interested in our work, you can refer to this published paper. Before going on, I first would like to thank the organizing committee for kindly offering an oral presentation here. I also would like to thank my collaborators contributing to this research. Here is an outline of this slide. Let us first see the background. I will introduce the background from this possible underlying integral systems, nearly integral systems, and finally to a non-integral systems. The underlying picture will be first contributed by the phonos without interactions that suppose ballistic thermal transport, and the phonos interactions, and the phonos finally phonos solitors and phonos discrete risers interactions. There may be two low bound lines to classify these different mechanics. That is the KAM and 0 and the weak and strong chaotic slows. With this possible underlying picture in mind, let us now see the recent central theoretic issue for thermal transport. Despite many efforts in the past decades, researchers still want to know what is the necessary and sufficient condition for free slow valid, and if yes, what or no, what are the underlying mechanics? The free slow states that the heat current is proportional to the temperature gradient with the thermal conductivity being constant in the thermodynamic limit. This issue is of fundamental importance. It's because this many-body non-equilibrium transport problem is one of the central theoretic issues in non-equilibrium thermostatic physics. It is also relevant to the experimental measurement of thermal conductivity in low-dimensional nano systems. For example, here gives two examples. Here is a measurement of heat conductivity in one-dimensional nanotube to these famous papers. And here is the measurement of two-dimensional graphene. Now we understand that despite the Fourier law is very famous in one-dimensional moment conserving systems, it has been generally realized that the Fourier law is not always valid. Instead, a length-dependent thermal conductivity will be seen. That is, the thermal conductivity will diverge in a parallel with the system size. Here, alpha is the divergence exponent. This enormous thermal transport is usually related to the enormous Lagrangian spread of energy and heat. And also, it's related to the enormous decay of the total heat current time autocorrelation function. With this correlation function and based on the Green-Kubo formula, one can derive the thermal conductivity. Here we note that the Fourier law indicates that the decay of this correlation function is potential, and the enormous thermal transport indicates that a long time tail of this correlation function. So we understand that for a general one-dimensional systems, the transport is usually super diffusive. That means the exponent like this. There is also another type of transport that usually called ballistic thermal transport, which usually takes place in integral systems like the focal chain and harmonic chain. There is some evidence for this to support the ballistic thermal transport. For example, for harmonic chain, the temperature profile of this harmonic chain in the center, it will be flat. Also, we can detect the heat and energy correlation function of this integral systems, such as for harmonic chain, its energy correlation function is a U sharp, and in another complete integral total chain, its correlation function is more complex, but both correlation function will follow the ballistic scaling, which is evidence for ballistic thermal transport. Here is the ballistic scaling for this correlation function for different time. Okay. Now the things become more interesting when one moves to the systems with long-range interactions. In particular, in 2017, the author of this paper have included long-range interactions into the traditional FPU model with nearest level interactions and found that the system can support ballistic thermal transport. In my opinion, this is quite strange since the system is still non-integral. So why someone can see this ballistic thermal transport? This then raises the following questions. Is this result true? If yes, are there any new excitations that can support this kind of ballistic thermal transport? But anyway, this interesting results seem to suggest new direction for theoretic study of thermal transport in long-range interacting systems. Finally, I also wrote that actually studies of long-range thermal transport in long-range interacting systems is not an easy task, even by numerical simulations. Now, bearing the above open questions in mind, let us now see the relevant model. Here is the Hamiltonian for long-range interacting FPU model. Here is Hamiltonian. Here is the kinetic energy, and here is the potential energy. In the nonlinear term of the potential energy, we include the long-range interactions. That means the strength of this sigma denotes the range value of the long-range exponent. For more details, you can refer to these papers. We will mainly focus on the case of sigma equal to 2. This is because the ballistic thermal transport was just found in this case. That means the thermal conductivity will diverge with the system size of a power law exponent to be 1. However, our viewpoint is that this strange result should be result from the problem of using fixed boundary conditions when idling the UV thermal bus. Here, the UV thermal bus, it means that we added 2 thermal bars with different temperatures to the left and the right-hand side of the chain. I think this setup will cause the system to be truly long-range interacting systems. Actually, this system is surely non-integral since the interaction is nonlinear. Here, I also showed the previous the setup of a previous study. Indeed, he added two small bars to two ends of the chains. Indeed, under sigma equal to 2, he found that the temperature profile is flat, which is evidence for ballistic thermal transport. Indeed, he found that the thermal conductivity diverges with the system size n of a power law exponent 1 under sigma equal to 2, which is also evidence for ballistic thermal transport. It may be also worth noting that there is a PRL paper in 2016. The authors found tail-free moving discrete brightness under 0 temperatures, which seems to support the above ballistic thermal transport. Now we see our results. However, we choose another boundary condition, that is the periodic boundary condition. With this boundary condition, we also use another thermal bars like reverse line equilibrium molecular dynamics method. This condition and these thermal bars will long change the system properties. So with this, we found that the divergent exponent is about 0.7. It is still super diffusive. To show this, we can see these pictures. Here presents two cases of sigma equal to 8, sigma equal to 2, and sigma equal to 8, which represent the long-ranged system and the conventional and short-ranged systems. For sigma equal to 8, we found well-behaved temperature gradient, and we almost recovered the divergent exponent in FPU model with nearest coupling. However, for sigma equal to 2, we still find well-behaved thermal gradient, even this temperature gradient, temperature gradient is smaller than the case of sigma equal to 8, and we found this very well divergent behavior, which indeed supports the super diffusive thermal transport. With this new finding, we now provide some evidence for the underlying mechanics. We first found that the heat spreading in these systems will support a new sharp. We also present two cases, sigma equal to 2 and sigma equal to 8. For the short-range case, we can see there is the Levy-Volk density, which is 3 peaks. When one uses this scanning formula, we can get a scanning exponent that indicates the super diffusive thermal transport. However, in the case of sigma equal to 2, we find this kind of sharp heat spreading function. In particular, in the center of this density, we showed a planeful. It usually shows in some ballistic thermal transport. But if one scan these densities in different times with this formula, we find a scanning exponent, gamma. This gamma scanning exponent can be related to the divergent exponent alpha by this formula, by the Levy-Volk theory. As we can see, it gives alpha to this value, which is very in good agreement with our above observation. Second, we conclude that this system may be weaker, non-integrable. Usually, one can measure the system's maximum diaphragm exponent. Indeed, previously, some researchers have found that the exponent depends on the parameter of sigma. And fortunately, the case of sigma equal to 2 is the minimal value. But it does not mean that the systems is integrable, which can support ballistic thermal transport. View is we just estimate this exponent versus system size for 3 kinds of systems. That is the case for sigma equal to 8 and sigma equal to 2, and another completely nonlinear and total systems. As can be seen, the value of exponent for sigma equal to 2 is just lying between these two cases. So it surely indicates that here the systems under sigma equal to 2 is a non-integrable systems. Compared to the traditional system with short-range systems, so it may correspond to a weaker non-integrable systems. We regard it to a weaker non-integrable systems. Third, we have also examined the system's tail-free moving discrete process dynamics. We use numerical simulations. We compare also 2 cases of sigma equal to 8 and sigma equal to 2. For the case of short-range systems, we found that the moving discrete process velocity sometimes can appear. But in the case of sigma equal to 2, it always, the dBs always keep their velocities, which indeed supports the observation in this PRL paper at 0 temperature. Of course, here we also under 0 temperature systems. However, these 0 temperature dynamics can actually not explain the valid temperature systems thermoconduction behavior. To further justify this, we just follow this paper to plot the spatial and time distribution of energy along the chain under a fixed temperature, such as temperature to be 0.5. In particular, we compare the two-time scale dynamics. In a short time, for both cases of sigma equal to 2 and 8, we always see moving excitations like this, which may suppose the system's ballistic thermal transport in a short time. In a long time, in the case of sigma equal to 8, these moving excitations will almost disappeared. However, in the case of sigma equal to 2, these moving excitations can still be identified. This may suppose that in the finite temperature systems, these discrete processes will have weak interactions. So this supports the observation of the divergent exponent. Finally, we also give another additional evidence of the total heat current correlation time functions. Here also 2 cases for comparison. For the case of sigma equal to 8, we almost recovered the traditional results for FPU model with nearest label coupling. However, in the case of sigma equal to 2, we clearly see a very slow decay of this correlation function, which then suppose a new type of super diffusive thermal transport in the case of sigma equal to 2. Now I think I am almost finished my work. Let us give a summary. In summary, we have provided convincing results for thermal transport in long-range interacting FPU systems. Further, we have reviewed that the underlying mechanics can be related to systems' low heat diffusion process and weaker line integrability and peculiar moving discrete process dynamics. That's all, and thank you for your attention.
Thank you very much. Please, any questions? Well, maybe I will ask, there was a slide where you showed the evolution of the heat profile, and there was the formula that alpha is equal to 2 minus gamma, where gamma is kind of coefficient. Yes, this one. Thank you very much. So do I understand correctly that alpha is the parameter of the Fermi-Pasta-Ulam interaction, of nonlinear interaction?
No. And alpha is the divergence exponent just here.
Ah, this is the rate of divergence.
Yeah.
But this is actually for Fermi-Pasta-Ulam chain, yes? So this result. I mean, this slide which you have shown. Not this one, but where this formula was written. Alpha is equal to minus gamma. Can you show it, please? This one. So, and here you have this profile evolution. Yes, I hear. Here you have this profile evolutions for Fermi-Pasta-Ulam chain, yes?
Maybe the light bulb is not very good now.
Okay, probably we have some connection problem. So anyway, I think we can then discuss it later on. And now, thank you. Let us thank Professor Xiong for his interesting presentation.